All right, guys. So it might be a short lecture, it might be a long lecture. We'll see how well you understand. So we'll speak about some important inequalities, the connection between expected value and variance and estimations of probability. So the very first part is Markov's inequality. And Markov's inequality states that if I'm dealing with a positive or non-negative random variable, then for any alpha bigger than 0, the probability that x is bigger than or equal to alpha is less than or equal to the probability, less than or equal to the expected value divided by alpha. So the expected value does allow me to estimate something about the probabilities, okay? Let's see why this is true. So first, you can try to take alpha and multiply it by the probability that x is bigger than or equal to alpha. And that's the same as alpha multiplied by the sum of all the probabilities that are not 0, where the xk are bigger than alpha, right? And this entire sum is clearly less than or equal. If I just replace the alpha by the bigger xk's, this summation is bigger. You agree? And because the random variable is non-negative, if I include all the other xk's with their probabilities, I'm only growing my sum, and then I get the expected value. So you see, this quantity is less than or equal to this quantity. So if I divide by alpha both parts of the inequality, I get the Markov inequality statement. So that immediately allows us to go through Chebyshev's inequality. If x is a random variable with mean mu and variance sigma squared, then for any value k bigger than 0, the probability that the difference between x and mu is bigger than or equal to k is less than or equal to sigma squared divided by k squared. And the reason this is true, it follows very quickly from Chebyshev's inequality. Think about it. Probability of x minus mu in absolute value bigger than or equal to k is the same as the probability that this number squared is bigger than k squared. Yeah, if I square it, I mean, nothing is changed. I can just square it. Squaring a bigger number will keep the proportion, right? So we have this. And now what do you see here? That's the, by the previous inequality, by Markov's inequality, this means that we now have a non-negative random variable. We take the expected value and divide by k squared, right? We just do for whatever positive random variable, we just take the expected value and divide by k squared, and that gives us an upper bound, an upper estimate. But the expected value of x minus mu squared is nothing more than just variance of the random variable x. So and that's what our sigma squared is. So variance of x, it's over k squared is sigma squared over k squared. So here is a simple example. Let's see if you can figure this one out. Suppose that in a bakery, the number of cakes produced is a random variable x, and we know that by conducting experiments, I suppose by seeing it, that the mean is equal to 50. So I mean, naively, I just imagine what you do is you run the statistics, you sum the average, you just calculate continuously the average every day until the average starts to be pretty much 50. You don't see a difference between 50 and something else. And that's how you know that the average is 50. Right? You did it a year, maybe 2 years, 3 years, and eventually you see that every day you update the average, it just stays more or less at 50. So what can you say about the probability that this very day 75 cakes or more will be produced? Oh, and Andrew, great, glad to see you, or at least your avatar. Regarding your last question, I think I can give you an example where variance, it's a simple example, where variance and expected value are the same, and that's not Poisson distribution. That's pretty simple. You can just take, I think, x equal to 1 with 50 over 70. Yes, Elahi, you are absolutely correct. Right, and then for part B of this problem, if you now know that the variance is 25, what can you say about the probability that between 40 and 60 cakes are baked? Yes, well, that's something we'll check for in a moment, right? 70 or 75 looks to me similar, right? So let's do problem A. So I get, sorry, not 70, but 50 over 75, right? Because I said probability that x is bigger than or equal than 75, not just 70, right? And that's by Markov's inequality. It's the expected value of x, the average here, divided by this number, 75. So that would be 50 over 75 or 2 over 3. And for B, because I now have variance, I can estimate what happens, what's the probability of baking between 40 and 60 cakes. So that would be, well, if x is between 40 and 60, then x minus 50, the average, x minus the average is between minus 10 and 10. And that means that the absolute value of x minus 50 is less than 10 here. Now, the probability of that happening is less than or equal to 25 over 10 squared, which is 1/4. Okay. So let's talk about the weak law of large numbers. All right, so the weak law of large numbers states that if we have x1, x2, and so on, we have identically distributed independent random variables, then we can try to calculate the likelihood that the average of those variables is going to be different from mu. Mu is the expected value of the random variable. And the probability that this is bigger than epsilon will tend to 0 as n goes to infinity. That's what the weak law of large number states. We will explain in a moment. Okay, so do you understand? So each of them is independent and identically distributed. The expected value of each of them is mu. And then what happens if we take the sum and divide by n minus mu? What's the probability it will be bigger than some number epsilon? And that probability will go to 0 as the number n goes to infinity. And that speaks about, the number n speaks about sampling, right? So basically x1, x2, x3, it's how many times I perform this experiment, and those are individual outcomes. So if I take the average of individual outcomes, I will find as n grows that it's very likely to look like the average that I predicted for the expected value. Okay, so why would that be true? Well, first of all, I calculate the expected value of a sum of n of the identically distributed variables divided by n. So I calculate the expected value of the average. Now, expected value is linear, so I'm able to factor 1 over n. And then I'm able to calculate the expected value of each outcome individually, which happens to be m. So what I have is 1 over n multiplied by n times m, which is my average, which is this m. Now, since the xk are independent, covariance between any two different x's will be 0. Right, we proved that in some lecture before. The covariance is 0, which means variance, first of all, variance of this average, I can always factor a constant out, so it will be 1 over n squared, the variance of the sum of those variables. And because they are independent, variance of sum equals to sum of variances. So that's not true in general, but it's true in this particular case. Yeah. So the sum of the variances, and what I have is 1 over n squared times n times sigma squared, because the variance of individual one is just sigma squared, and I have n of them. And therefore I have sigma squared divided by n. That's when I divide the variance by n. So what happens here by Chebyshev's inequality, look at it, right? So if I want to predict what's the probability for a fixed n, what's the probability that this quantity minus mu in absolute value will be bigger than epsilon? The probability it will be bigger than epsilon will be what? 3/4. Well, I might have written, because I need to check that problem again. I might have made an error, right? You need to, I think you need to, yeah. So we'll get to it possibly later. Let me just finish with this thing. So yeah, so by Chebyshev inequality, right? We know the variance of this average, and yeah, we know the variance of this average. By Chebyshev's inequality, it will be the variance divided by this number squared. Yes, which means the variance is sigma squared over n, and when I divide by this number epsilon squared, that is going to be the estimate, the upper estimate for this probability. So the probability that the deviation of the average from my theoretical mean is bigger than some number epsilon will be sigma squared, the variance, divided by epsilon squared, and also divided by n. So let's try to understand how this problem works. Okay, so suppose this is what we want to know. So we have a fair coin, right? And we are going to toss it a bunch of times, right? You obviously think that if I toss it enough times, the average number of tails will be half the number of tosses if it's enough many times, right? So the question is, how many times must we toss this coin so that I will be getting average within average equal to 1/2 within 1/10 of a unit. That is my average. When I run the experiment, it's either 0. It's a number between 0.4 and 0.5 99% of the time when I run the experiment. You get my question, right? So how big is my sample? How many times must I toss this coin so that the number of tails obtained, divided by the total number of experiments performed, will be a number between 0.4 and 0.6 99% of the time I perform this experiment. See if you can calculate it. There must be a special date, 25 participants. All right, guys, did you understand what the weak law of large numbers states roughly? No, right? I can re-explain it. It's very difficult. So the idea is this, right? So the random variables, they're random, they're not predictable, right? So every time you you perform the experiment, you get a different outcome, correct? So what's the idea of them being identically distributed? So x1, x2, x3, etc. are identically distributed. So that is the same as running the same experiment again and again and again. Yes? So x1 means the first time I run the experiment. x2 is the second time I run the experiment. x3, third time I run the experiment, and so on. Yeah? So that's why, that's because they're identically distributed. And I'm running the experiment independently. Yeah? So now, if I know something about this random variable, so for example, in this case, I am dealing with a fair coin, right? Metaphysically, a fair coin is one that has no preference to land on heads or on tails, right? So it doesn't have any preference. So if it doesn't have any preference, given enough many trials, the coin will land on tails exactly half the number of times, right? If the number of trials goes to infinity. correct? So I know the expected value is going to be 1/2, right? What is the expected value is essentially the number of, in this case, the number of trials. The number of successes, I'm sorry, divided by the number of trials. Yes? Yeah.
A quick question. I'm trying to understand why it should be greater than epsilon.
It was why greater, because what's the idea of it? What we are using is essentially Chebyshev's inequality, or there are many names. You can all go all the way back to the to this Markov inequality, right? Let's go up. Let's see where it all begins, right? The entire idea is that if I'm dealing with a positive, here it is, right? If I'm dealing with a positive random variable, then the probability I have it bigger than or equal to some number alpha, it's going to be the expected number of x divided by alpha. Why do I want bigger than or equal to? Because I want an upper estimate in the probability. I want an upper bound. So here is, if you look at this calculation, what happens here? We have alpha times the probability x is bigger than alpha is the same as alpha multiplied by the sum over all probabilities where xk is bigger than or equal to alpha. Do you see this, right? And that I'm basically trying to reconstruct expected value out of probability in essence, right? So what happens here? I can move the alpha in here. I can take this alpha and move it past the summation sign, and then I make the sum only larger because alpha is assumed. That's why we have greater. That's the most important part. X is greater than alpha, which means I can replace alpha in each instance by the xk. You see? If it were less, I could not. I would have made the sum smaller. My goal is to use expected value as some sort of upper estimate for the probability, right? So here, that if I move alpha in here, I'm only making the sum bigger by replacing the alphas by the xk's, because the xk are, by the very definition, are bigger than alpha. And then I have this summation. And now this sum is bigger than alpha times the probability x bigger than or equal to alpha. And then the sum is complicated to calculate because it's different from different values. But I also know that x is positive. So I just then add in all the remaining probabilities with the remaining x's, some of them possibly smaller than alpha, and I get expected value. But because x is always positive, that's an important assumption. If x is not always positive, that might not be a correct estimate. Since x is always positive, I know that the expected value is now a bigger sum than alpha times px bigger than or equal to alpha, right? And then I divide everything by alpha. I now have that probability that x is bigger than or equal to alpha is less than or equal to the expected value divided by alpha. So here is where that alpha is coming in here, right? So instead of alpha, I'm using epsilon here, just a different symbol, right? So what you have here is what's an absolute value is definitely a positive, or to be precise, it's a non-negative random variable. You see, because I took absolute value here. So that's like the x from Markov inequality, right? And the probability that it's going to be bigger than or equal, can that equal, doesn't matter, right? Bigger than epsilon is estimated by the expected value of this random variable divided by epsilon squared, well, divided by this quantity. But it's not convenient to estimate the expected value of this number. So what I do is I square it, and the expected value of this squared is the variance. That's the idea. Yeah.
Thank you.
Yeah, sure. That's the idea. So so that would be this number. So epsilon is just whatever number you select, right? Epsilon is how precise do you want the average, right? So how well do you know this difference between 1/2 and something else? So in our case, epsilon is 0.1, right? Because basically I'm thinking that, well, it's reasonably close if my numbers jump between 0.4 and 0.6. Okay. If I want bigger precision, I must possibly increase the number of trials. Okay, so yeah, so go over those calculations. The notes are also posted, and we'll repeat it if you need. Okay, so you see what you have to do here, right? So this tells you the tolerance, right? Basically, I want, It's like in the delta epsilon proof, I want my limit to converge to mu. And how do I understand that convergence is happening? Is that I no longer can distinguish the actual outcome from the theoretical outcome, right? So how do you know that 1 over n, for example, goes to 0? If you select n large enough, eventually it looks to you like 0, right? It's not a true 0, but it looks to you like 0, you cannot distinguish it. And if it looks to you like 0, it doesn't have to look like 0 to somebody else, right? So when you say looks to like 0, you want to be precise about it. With what tolerance, right? So the smaller the epsilon, the more it looks like 0, right? So because those outcomes are not predictable, so here you're calculating the probability that you will be able to discern the actual average from the theoretical average. You will actually be able to notice that they are different. So epsilon is your ability to notice that they are different. And the probability here is estimating how likely will that actually happen. That you say, oh, it's actually not what the average I thought it will be. Does it make it a little bit more sense, guys? By your faces, I think no. I only see what 3 faces. Okay, so talk to me. Where have I lost you guys? Delta epsilon. Are you well versed in delta epsilon? We can talk even about that afterwards. Right. So it's a kind of modified delta epsilon proof, right? So in delta epsilon, do you know what epsilon signifies? So it signifies how much can you tolerate a deviation from the theoretical outcome. Okay. So for example, if you can tolerate a deviation of 1 over 100 for 1 over n, right? So that means that if you calculate 1 divided by 1, 1 divided by 2, y divided by 3, you make those calculations. When do you stop seeing that it's not 0? You stop seeing that it's not 0 when the numbers are within 100th away from 0, right? So if you select, it means what? For the sequence 1 over n, if you said epsilon is equal to 1 over 100, it means that starting from the 100th term onwards, you're no longer able to tell those things apart, because 1 over 101 is already smaller. It's closer to 0 than, you understand? So that's when you no longer can tell that it's not 0. So if you say epsilon, in my case, is, so it's in some sense a way to quantify your subjective, abilities to tell the difference between theoretical limit, what theoretical value, and what you actually get. So, right. So for that definition, right, you would, if epsilon is equal to 1 over 100, then starting from the n equal to 101, 102, and onwards, you no longer, your conclusion is that you get 0. Somebody who is better at telling the difference apart might select a smaller epsilon. Okay, so what is this, right? So for everybody, this epsilon exists, right? So for example, in your calculator, epsilon will be 1 divided by maybe 10 to the 8 if it makes if it can display 8 digits, for example, right? So it might be a very low epsilon. A better calculator can discern even more, right? But everything has its own epsilon, right? So for example, if your calculator displays the number 0.5 and then a bunch of zeros, right? All of them are zeros. Is it 1/2? Not necessarily, because maybe beyond the screen, here's your screen, beyond the screen, you would see another number. But within that screen, you see 0.5 and a bunch of zeros. So you conclude that what you're looking at is 1/2, but you might be incorrect. Understand? And that's your tolerance. The blinders around the screen is your tolerance. So this epsilon represents a tolerance. Okay, so the weak law of large numbers predicts the following. It predicts that if n, it's actually more complicated than a regular delta epsilon proof, right? It's much more complicated. But what it predicts is this, right? So you when you increase the n, if you increase the number of trials, the average that you calculate here, you see I'm pointing to the average. That's the actual average that I calculate. So x1 is the outcome I got in experiment 1. X2 is the outcome I got in experiment 2, and so on. Xn is the outcome I got in experiment n, and then the outcomes are either 1 or 0. 1 or 0, right? So 0 if I did not get tail, and 1 if I did get a tail. So I add them up. That's the sum of tails that I got, and I divide by total number of trials. Yes, that would be the average number of tails obtained for this experiment with n procedures. Yeah. Good. So so how many trials do I need to perform so that I am not likely to see? That's what this is really saying. It's giving you for all distributions, right? It tells you how to estimate how many trials do you perform so that you are not going to be likely to see a deviation, right? So in this case, the probability that the difference is bigger than epsilon means the probability that you can actually detect that your average is not the theoretical average when it's bigger than epsilon. Understand? So if your calculator can display 8 digits, then your ability to detect a difference between 1/2 and something else is your epsilon would have been 10 to the minus 8, for example, right? Because that's how many digits we have. Yeah? Do I begin to make sense, guys? So, yeah. So epsilon for this problem is 0.1. I selected not the biggest epsilon because you will see that you know, if you use this estimate, it's not necessarily a sharp estimate. It's ubiquitous for all distributions, but not necessarily sharp, right? So if I select epsilon equal to 1/10, it means what? It means that for you, any number that is between 0.4 and 0.6 looks like 1/2. So you're not very, how do you say, sharp in your eyesight. 0.4 to 0.6, all of them look to you like 1/2. You cannot tell the difference. I mean, you look at me, I can tell the difference between 0.4 and 0.6 and anything in between and 1/2, you might say, right? But you cannot tell the difference between 0.5 and 0.5000000 and maybe 7 afterwards, right? Somewhere far, right? So it's a matter of how sharp can you see. Okay, if you want a better number, take maybe 10 to the minus 5. That means 5 digits. It looks like 1/2 to within 5 digits. You understand? So I just took something that looks like 1/2 to within within 1 digit, right? So it's very kind of, it's between 0.4 and 0.6. And I want n to be large enough so that 99% of the time you will see. Yeah, so 99% of the time you will see that there is no discrepancy detected, giving this very weak ability to detect the difference between 1/2 and the actual number, right? Understood? So let's try to calculate it together. Let's see. Yeah, so Andrew, you nailed it. You say, Andrew says, the left part of this estimate, this left part, is the probability that that I get an average. This means what? For my example of 0.1, this means that I get an average that is bigger than 0.6 or smaller than 0.4, something that I can detect, right? I was like, oh my God, it's 0.3. Now I know it's not 1/2 because within my bounds of my bounds of detection, 0.3 is too far away from 1/2. Okay, and 0.7, let's say, is too far from 1/2. Anything outside, you say I have this bound. Anything below 0.4 is too far from 1/2, and anything above 0.6 is too far from 1/2 for my tolerance for this epsilon. Good, you follow? And that is estimating the probability. So I want the probability to be 99 out of 100, right? So in other words, if you run this experiment on average 100 times, you will detect a deviation once. Make sense? So you run it 100 times and only once do you detect some difference. So in essence, you're always getting scores that are 0.4 or 0.6 or anything in between. It could be a range of scores, but it does not jump outside of this interval. Yes. So the higher the n, so you have several controls. You can select a tolerance, right? So for any particular tolerance you select, eventually, if n is made larger and larger and larger, this probability diminishes. It becomes less and less observable because you see, for a fixed epsilon, the variance is not doing anything. It's just a constant number. The epsilon squared is not doing anything, but the n is growing. So this probability will become very small. Yes? So I need to figure out how big should be n so that this probability is what? So this probability is smaller than 1 over 100. Does it make sense? I want this probability to be less than 1 over 100. In other words, less than 1 in 100 chance that I will detect a discrepancy between 1/2 and the actual average I'm obtaining, right? And this is telling you the ability to detect discrepancy, right? So in this case, I set it rather low. I set it 1 over to be 1 over 10. The answer, no, we need to calculate sigma. The answer has to be a number, right? I need to know the answer. In this case, I want an n. So let's try to do it together, right? So again, right, I told you what the xk's are, right? The xk's are 1 if I get tail on the kf toss, and it's 0 otherwise. So what is the expected value? The theoretical expected value of each xk is clearly 1/2 because coin is fair. It's 1/2 times the probability. So it's 1, sorry, times the probability of getting it to equal to 1, which is 1/2, plus 0 times the probability of getting it wrong, which is 1/2. So I get that the expected value is 1/2. Are you with me, guys? I got you to understand. Yes.
Mm-hmm.
Yes. I'm very worried about the strong law of large numbers. That will be very confusing, right? But let's see if we get the weak one right. So what then? So now I calculate the variance, right? I calculate the expected value of xk because it will be useful in calculating the variance. Now, what's the variance of each xk? Now, that would be the expected value of xk squared minus the square of the expected value xk. But the expected value of xk squared also equals to 1/2. You see that? Because it's 1/2. Sorry, it's 1 squared times 1/2 times 0 squared times 1/2, which is still the same number. So it's 1/2, and this is 1/2 squared. So I have 1/2 minus 1/2 squared, and I see that the variance is 1/4. The variance of each individual trial, so basically, is 1/4. On average, I will get 1/2 as my as my outcome, right? And then I have variance is 1/4. Are you good with me, right? So now by weak law of large numbers, here is what I am trying to do, right? So I want the probability that x1 plus all the way to xn divided by n minus 1/2. The formula for variance, Andrew, I'm not sure I understand your question. It sounds like something interesting that I should address, but I'm not sure I understand. What do you mean by constraints? The reason we apply variance and not expected value here is look at the setup. It's the variable minus the predicted average for it. And you see, if I square it, it will be variance. If I put a square here, that would just be variance. That's why if I square it and I square this, really, right? I have to calculate the variance of x1 plus xn divided by n. So, yeah, let's see. So this, so variance, Andrew, variance is always this, right? Variance is always the expected value of the random variable, of the square of the random variable minus the square of the expected value. So it's always the formula you wrote. So where are we? So basically here is what happens, right? So by the weak law of large numbers, all I have to do is I have to take the variance, and the variance is what? You see, because they're identically distributed and I have n of them, the variance is 1/4 divided by n. Do you see that? We calculated it before in the proof. We calculated it over here, right? So I calculated the individual variance of one of them. Now, if I want to calculate the variance of the average here, that ends up being the individual variance divided by the number of variables I have. Okay, so from there I see the variance of x1 is, let's say, 1/4, and therefore the variance of this entire variable, so it's the sum divided by n, is 1/4 divided by n. Yeah, and then I need to put here, in addition, I need to have this number squared, the epsilon squared. So all those, you see, I would never remember those quantities. It's very easy, and on the other hand, to establish why this formula is true, right? So Romulo asked me some few lectures ago, maybe a long time ago, asked me why do you divide by n, or he said when he always divides variance by n. This is a reason for it, right? It's because I'm calculating not the variance of individual variable, but of this quantity. Okay, this sum divided by n is a random variable, because the average is jumping around. The average is going to be at one point one number, at another point another number. This number is jumping around. If I assume they are independent, then the variance of this whole thing, of this average, is the variance of one individual outcome, of one individual random variable divided by n. Okay, and we take this number and we divide it further by 1/10 squared. And what do we get? If I simplify it, it's really like 100 multiplied by 1/4, so it's 25 divided by n. And I asked this probability to be smaller than or equal to 1/100. Yes. So I want 25 divided by n to be less than or equal to 1/100, and that means that my n should be bigger than or equal to 2,500. You see, what this thing is predicting is the following: that if I'm going to toss a fair coin 2,500 times, I can be assured by this weak law of large numbers that my average will not deviate by more than 1/10 away from 1/2, with probability equal to 99 divided by 100. Right, 99% of the time my average will not deviate. Of course, some of you might be thinking, well, that's a very huge number of tosses. Shouldn't it be smaller? And again, right, this is not a theorem that applies specifically for tossing a coin. It's ubiquitous for all distributions, and because of that, it tends to overestimate the number of trials. Right? If you toss the coin this many times, you would think that it will be very accurate. It will be much better than the estimate. Right? It will be very likely very close to 1/2. So the weak law of large numbers in that case, it's like estimating that it's 99% certain that every single person alive is less than 20 feet. You see, so it's being very cautious and possibly exaggerating. Right? It's much more than 99% certain that every person alive is less than 20 feet. Right? But this gives you a ubiquitous value for all of them. Right? That means that you can be certain from this theorem that 99% of the time, if you throw the coin 2,500 times, then the average you will get is between 0.4 and 0.6. You understand?
Yeah, I have a question.
Go ahead.
Why don't you make it equal to 99/100 is less than or equal to 25/n, and then solved it?
Say it again. So here is.
Mm-hmm. Yeah, because you said it's 99% sure, and you said that
right, 99% sure, but that means that 99% sure that it will be between 0.4 and 0.6, right? But this is the probability that I'm wrong. That it's because you see it's bigger than 1/10. That means that the difference is more than just 0.5 plus 0.1, right? It's more.
Okay.
Right.
Okay.
Yes, we're not calculating, and again, right? This gives you look at the number, right? You would expect that you need far fewer tosses of the coin, and even with far fewer tosses of the coin, you would think that the average will converge faster, right? It's just the weak law of large numbers is not specifically dealing with one distribution. Since it applies for all distributions, it's much more cautious than it has to be in each individual case. You understand? It does not give you necessarily the most sharp estimate, right? I mean, what's the minimum number of tosses, right? I'm not claiming that this number is the minimum number of tosses to be that certain. I'm only claiming that if, according to this theorem, if you toss the coin 2,500 times, then you're not likely to produce a sum that is bigger than 0.6 or lower than 0.4. Okay, not likely, and you have an estimate of how unlikely it is. Does it make sense?
Yeah.
Right, and again, so don't be scared by this number. You might try the binomial approximation. So there is central limit theorem. There are other things that are much better to estimate how many coins we should toss for the probability of deviation to be small. Okay, but the weak law of large numbers applies to every distribution. As long as the trials are independent, it applies for any distribution, right? As long as the trials are independent, it will apply. Good? Yeah, so yeah, again, right? So now if this was difficult, wait until you hear the strong law of large numbers. God damn it, right? So here is what the strong law of large numbers says, and maybe before I prove, I will try to explain what might be a difference between them. I can tell you this, that I can explain what's the difference between them, and I still truly, even with my explanation, I cannot, practically speaking, tell you what's the difference. Let's say, because I mean, this has to do with measure theory. I understand what is weak convergence. There isn't one is called weak and another called strong. In measure theory, there is something known as weak convergence, and there is something known as strong convergence. Okay, and in that sense, I understand this theorem. But in practical sense, that remains to be debated. But let me tell you what this theorem states. So now we again have identically distributed and independent random variables. Again, the expected value of each individual random variable is mu. And we now claim the following: with probability 1, the limit of this quantity of the average, the limit of the average will be equal to mu. So what this is saying is this, right? If I continue tossing the coin forever, if I toss it 1, 2, 3 times, if I toss it forever, I will see 1/2 certain. But then again, right, with certainty, even this, because remember, I bothered you. I said if something has probability 1 of occurring, it doesn't mean it always occurs, at least not in the way I understand it, right? So that's why even that statement is not, it can be very confusing. But let's say for a moment, let's say this, right? So if you are going to continue with the trials forever, practically speaking, what does it mean to continue with trials forever? But if you continue with the trials forever, you will find that the average always converges to 1/2, right? If in the case of the coins, right? So before that, right, I let's say if I performed 2,500 tosses of the coin, well, the average is not going to be exactly 1/2. It might be, according to this estimate, it's not a very good estimate. It's a very kind of upper bound estimate. You're convinced that at least 99% of the time, the outcome is going to be between 0.4 and 0.6, right? What this is saying is that if you continue performing it forever, in the limit of this quantity will be getting closer and closer and closer to 1/2, okay? And to no other number. So every time you perform it, you just throw it more, and eventually you begin to see something very similar to 1/2, arbitrarily close to 1/2, okay? Let me try to scroll down and try to, before I prove it, it's a long proof, try to tell you again what's the difference between them. So here is again the example of a deterministic sequence, right? So look at the sequence 1/n. The sequence 1/n, converges to 0. And if you think about convergence, what you do is imagine that you have a detector, right? And the detector has a resolution epsilon, right? So for example, we mentioned, suppose the resolution of the detector is 1/100, which means that when the number is closer to 0 than 1/100, the detector tells you got 0, okay? And if the distance between 0 and the actual outcome is bigger than 1/100, the detector tells you did not get 0. Yeah, makes sense. So So here, when you imagine the experiments performed for the deterministic sequence, imagine you have this epsilon, right? So what you have is, and a machine is performing this. Apologies, somebody was noisy. So, and that somebody was my brother. God damn it. And he doesn't want to be muted. All right. So what do you have here, right? So suppose we have this this machine, and it's basically its resolution is 1/100, right? And what you see here, I mean, you are saying 1, 1/2, 1/3, but let's say what the machine is saying, 0 or not 0. Okay. So 1, will the machine say 0? No. 2, will the machine say 0? 3, will the machine say 0? What's the first number where the machine will say 0?
101. 1.
Yes, exactly. So you look down to the 101st row, and then you see 0, 0, 0, 0, etc. Right? All of them, the machine says it's 0. It's not correctly true 0, right? And then you think, okay, let me put a sharper, better detector. So I install a better detector. Now its resolution is 1/1000. When will it start saying that everything looks like 0?
1001.
Exactly, brilliant, right? So for this, so it could be not so simple to determine to do the delta epsilon thing, for different sequences. That's not the point. The point is when a sequence converges, then every detector will eventually, if you put it in a column, every detector will tell you it's the theoretical convergent value, right? So in this case, 0. So the machine will scan it, and starting from some row will just write 0, 0, 0, 0, 0, 0, even though it's not completely true. If you take a better machine, it will just start writing zeros later, right? If it's a better machine, maybe at a lower end, right? But all of them will tell you eventually that it's only 0. So it cannot tell the difference between 1/n and 0. Yeah. Now, what about another sequence? Let's consider the other sequence. In the other sequence, it's equal to either 1 or 0. So it's actually always equal to 1 or 0. Yeah. 1 or 0. So it equals to 1 if the number is 2 to some power. So it equals to 1 when it's 2 to the power of 1. It equals to 1 when it's 2 to the power of 2. It equals to 1 when it's 2 to the power of 3, right? And yeah, so you understand how the machine tells you get to convergence. It's only when it sees an infinite string of zeros that never is anything other than zeros, right? So yeah.
What about the value n equal to the power of 0? Then it should be 1, right?
Well, let's say we have here k will be starting from 1 and onwards, right? It depends on how you start. It's just a matter of setting it up, right? So I'm just considering 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, right? The point is this, right? So so then you see, let's say I apply this detector that has resolution 1/100 as before, right? Will it ever conclude that Bn converges to 0?
Can you repeat the question?
Yes. You see, you put the detector. So you put here on this column, you put the detector with resolution 1/100, epsilon equal to 1/100, right? So eventually, as you mentioned, starting from 101st entry, it sees all of them without any exception are 0. So the detector will tell you, okay, this thing is converging to 0 because it sees an infinite, unending, monotonous string of zeros eventually, right? Yeah. Now, let's say I put the detector for Bn. Will it ever see? Will it ever conclude that Bn converges to 0?
Probably not, because all the terms are just 1 and 0. They don't get any smaller.
Well, yes, it will. But so Josh says no, and you say probably not. But be precise. Right? The machine tells you that it's not zero when it basically is able to detect deviance from zero by more than 1/100. Right? And 1 is clearly a distance more than 1/100 from 0. So it will detect deviance from 0 infinitely many times. You agree? For the sequence. So Bn does not converge to 0. But in a sense, you can say Bn weakly converges to 0, like in the weak law of large numbers. Why weakly? Because think about it, right? If you run this for n very large, right? So eventually it's 2 to the power of 100, and the next time you see a 1 is 2 to the power of 101, correct? And the difference between them is huge. 2 to the power of 100 is a huge number, and 2 to the power of 101 is twice as far, right? So so first you see, look at it. First I have 0, so I have 1, and then I have to only move 1 unit, and then I see 1 again. But the distance between the ones, it grows and grows. They become very infrequent. Understand? You basically, you look everywhere you look, it's not likely that you will see anything other than the number other than 0, right? It becomes very unlikely. So Bn, in some sense, converges weakly to 0. Because if you run the detector in finite time, you understand? If let's say if you're a programmer, like possibly Josh is a programmer, right? You say check the sequence for, let's say, 100 terms or 1,000 terms or 3,000 terms of 10,000 terms, and then if you detect difference from 0, then say the sequence does not converge. And if you detect no difference, then say the sequence converge, right? Basically, you get tired. You see a monotonous string of zeros, and you want to terminate the algorithm. You want to say, you just quit it, it's 0, right? So that's what you call weak convergence. It's because eventually, if n is very large, if k is very large, whatever you like calling it, right? It's going to be very hard to detect that the sequence does not converge to 0. You have a much more precise way to describe it. It's just then I have to go through measure theory, right? So measure theory, a sequence might not converge anywhere. So you might have a function or a sequence of functions. They do not converge at any point, but to detect that they are not converging will be very difficult. Yeah? Do you understand? So that's one instance of basically why it's called weak law of large numbers and strong law of large numbers is for that reason, right? So the weak law of large numbers does not claim that so I'm actually lying, at least lying in the way it's in my head. I think it's much more confusing. But let's say what this means is that with certainty, every time you increase the number of trials, you eventually begin seeing the average. In the example, you begin seeing the number 1/2 eventually, right? So this is what the strong law of large numbers roughly is saying, that if you continue with the trials, eventually you're bound to see a number ever more similar to 1/2. More trials, more like 1/2, right? So certainly you will see that. Okay, and on the other hand, what's the weak law of large numbers saying? It's saying that you are just not likely to see a difference, right? So you have as you increase the sample for any particular distance, you are not likely to see the difference. Okay, notice this number is fixed. So any particular detector is less and less likely to see the difference. The probability goes down. Like it would go down for the Bn because they become very sparse, right? So the probability of noticing the difference just goes down. But you actually have infinitely many deviations, and the limit is saying that you will not have deviations at all, right? And once I explained this, my internet is a bit unstable. Can you still hear me? Yeah, I mean,
yes, loud and clear.
Yes, because you got stuck. Your video is not going too well. Okay, good. And having said that, the problem is that probability equal to 1, at least theoretically, does not mean that you actually see the outcome. Okay, remember we mentioned that, right? Although yeah, I mean, yeah, probability equal to 1 it doesn't mean that you actually see the outcome. So in that sense, while having explained it to you, I cannot claim that I truly understand it. right? I can understand when it's deterministic sequences, but not when you talk about probability, because again, right, probability is some sort of, to me, a metaphysical concept. So let's try to go through the proof, shall we? Are you with me, guys? You got stuck.
Yeah.
Okay. So no interruptions. You can see the screen because the video is froze. I'm not sure. Maybe the internet is crashing. Hello, guys. Yeah, there was a crash. So let's see. Yeah. All right. So you can see my screen. Everything works.
Yeah.
Cool. Okay. So let's try to prove this theorem. So we are going to prove it under an assumption that simplifies the work. You will see later why. So I am assuming that the expected value of xk to the power of 4 is whatever that number, it's less than infinity. So if I take my random variable to the power of 4, I'll get I'll get something less than infinity. So I will make yet another assumption that mu equals to 0. Right? At the end, I will explain that this assumption is not losing our generality. So then I will abbreviate by S sub n to be the sum of n random variables, x1 through xn. And Sn to the power 4 will be the sum raised to the 4th term. Okay. So I want to calculate the expected value of the sum raised to the 4th power. Okay. And I'm assuming again that the expected value of each of them is 0 and that they are independent. Okay. So so terms of the form. So if I expand it to the 4th power, I have all possible combinations of terms of the form. You know, one term from the first parenthesis, like in here, right? A term from one parenthesis, then any term from another parenthesis, then any term from third and fourth parenthesis. From any parenthesis, I have one x borrowed, and I multiply them out. Okay, so then I might have situations where every single term I picked is different from every other term, right? So let's say I pick xk, xj, xi, and xh, and they are all different from one another. So I never pick the same term twice. I never picked x1 twice or x2 twice. So just only one from each parenthesis, and they're all different, right? So if I picked x1 from here, I did not pick x1 from here, and I didn't pick x1 from here. They're all different, okay? Yeah. Good. So because they are independent, remember we had a proof of that for two of them. The expected value of a product of those independent random variables is the product of the expected values. Okay, that's something you should it has to do with multiplication, right? It's just the same as the case when you had two of them in covariance, right? It's a matter of multiplication, and what you need is to be able to factor the probabilities into products, which you can do when it's independent. So the expected value of this will be just the product of all of them, which, because they are the same, is just like the expected value of one of them to the 4th power, but the expected value of any one of them is 0. They all have the same distributions. So terms that are different will not contribute anything. Similarly, I can have a situation where I have one variable picked twice. You see, so from those parentheses, maybe I picked x1 here and x1 here, and the other two I picked that are different from one another, right? So I could have this situation, and the expected value will be the expected value of xk squared times the expected value of xj times the expected value of xi. Even though I don't know the expected value of xk squared, I know the expected value of xj is 0, right? So because I have one of them raised to the power 1, the entire thing becomes 0, because it will be still the product of the expected values of random variables that are not dependent on one another. So I have here xk and xk. So xk depends on xk, obviously. Okay, so they are all 0. And in general, if I have any term here where at least one of the variables is raised to the power 1, the expected value of the corresponding product will be 0. Does it make sense? So the only things, if I just expand x1 all the way to xn to the 4th power, the only when I calculate expected value to be the sum of the terms, the only terms that I need to consider, the only things that survive, are where I have even powers, only even powers. So I have maybe something like xk to the 4. I picked 1 4 times, or I picked 2 pairs, 1 pair and another pair. That's the only thing that I cannot conclude the expected value is 0. Okay, so the expected value of this guy it's true that it's the expected value of the first variable times the expected value of the second variable, but they are squared. I no longer know that this expected value is 0, because if it's 0, you know, I had negative values, I had positive values, I had all sorts of things like that. Okay, if it's 0 and it's not constantly 0, then I must have had positive and negative values. But when I square, I no longer have negative values. So there is no reason to think that this will be an expected value equal to 0. So this is probably not 0. Unless it was identically 0, the expected value will not be 0. Okay, so then what do I observe? So here is that expansion. So I take the expected value of Sn over n, the average to the 4th power. That's the same as 1 over n to the 4th, the expected value of Sn to the 4th. And what survives is the sum from k equal 1 to n of the expected value of each single variable raised to the 4 power, and plus the summation which combines every pair. And because they are identically distributed, the first part I can replace simply by n times the expected value of x1 to the 4th. Interrupt me, guys, if you don't understand. So this is n times the first. And this sum I can replace as follows, right? So here I have 2 pairs, right? So if I have 2 pairs, which 2 pairs? I have n choices. I need to pick 2 of the random variables that are going to be paired. So there are n choose 2 pair combinations. And then we multiply it by 4 choose 2. Why 4 choose 2? Because if let's say I picked x1 and x2. Let's say I picked x1 and x2. So how could I have picked x1 and x2? I could have picked the smaller indexed variable for maybe first and second, and then x2 was picked from third and fourth, right? So there are 4 choose 2, because which of those 4 parentheses contributed the smaller of the variables, which contributed the larger of the variables, the larger indexed variable, right? They're identically distributed. So in total, n choose 2 for number of combinations of indices, n choose 2 combinations of indices times 4 choose 2 of ways of producing those indices. So altogether, now I can replace this expected value. Notice the expected value of x1 squared times x2 squared. They are independent. x1 squared is independent of x2 squared. Yes. So that would be the expected value of x1 squared squared. So altogether, this estimate is 1 over n to the 4 times n expected value x1 to the 4th plus 3n times n minus 1, the expected value of x1 squared squared. Okay. Now I'm going to, here is where I use the 4th power. I'm going to estimate those numbers. I'm going to say that this number here is no more than m. So if I calculate the variance of x1 squared, the variance of x1 squared is the expected value of x1 squared squared, or the expected value of x1 to the 4th, minus the expected value of x1 squared and the entire thing squared. Sounds like very confusing, right? You're probably lost consciousness by now, right? Too little oxygen. So because variance is always non-negative, it means that the expected value of x1 to the 4th must be bigger than or equal to the expected value of x1 squared squared. So in other words, this number and this number can both be replaced by the letter m. It can be replaced, but I'm estimating a sum. So here is what's happening. So in particular, the expected value of the average to the 4th power is less than 1 over n to the 4th times n times some number m plus 3n and minus 1 times n. So I have an estimate. I have an estimate for this expected value. And now what I notice is that this estimate creates a convergent series. So let's say if I add up all the expected values for all the n from n1 to infinity, I add those expected values, I will get summation less than infinity. Why? Because look at it, right? The summation is bounded by the summation where n goes from 1 to infinity of this thing. And this thing is, so it's m divided by n cubed. That's a convergent P series. And this can be estimated as 3m divided by n squared, which is another convergent series. Yeah. So this summation is less than infinity, which means that the expected value of Sn to the 4th goes to 0. Do you follow me, guys? No. Yeah, I figure, right? I'm thinking, when are they going to tell me that old men, I don't know what you're talking about?
Can you explain how you got from? I understand where you got from m plus 3.
Perhaps here's what I will say, right? So those are all algebraic procedures. What's the idea here, right? The idea is to show that, look at it, right? Is to show that this sum, look at it, the expected value of this is a pretty complicated looking random variable, right? I'm claiming that Sn over n to the power of 4 is going to 0 rather fast, right? It's going to 0 rather fast, right? And with probability 1. And how I want to claim it is that I want to claim that the expected value of this sum is less than infinity. This is basically the starting point. If I claim that the expected value of this random variable is less than infinity, it must mean that that the probability that with probability 1, this sequence will go to 0. Remember, my average is assumed to be 0, right? With probability 1, this average will go to 0. Why with probability 1? Because if the probability that this equals to another number, not 0, is not 0, if the probability that it's not equal to 0 is something, then it's possible that this random variable takes infinity as one of its values. So this random variable might take real numbers or infinity as one of its outcomes, right? And we only need to consider outcomes that can be taken with non-zero probability. So if this random variable has a non-zero probability of being equal to infinity, that will mean that the expected value is infinite, because the expected value is bigger than at least one term, infinity times the probability of getting infinity. Okay, but if I have, no matter how small, if I have some probability of getting infinity, the expected value will be infinite. So if I show that the expected value is less than infinity, that means that the summation never equals to infinity. With probability 1, it does not equal to infinity. And that means that with probability 1, the terms of the sequence will go to 0. Okay? And if they go to 0 with probability 1, then I can drop the 4 power. Then that means that this will go to 0 with probability 1. Okay? And everything else is just proving that the series converges. It's just proving that this expected value is less than infinity. It's kind of subtle idea. And you can prove it with other assumptions. You don't need the power 4. It's just the proof will be more difficult without that assumption. Okay? And in the general case, you can see that you can just set yk equal to xk minus mu. You can always reset the average to be equal to 0 without changing much about the distribution. Well, thank you for suffering. Right? You can always leave whatever class.
To come back with many questions in our Monday class.
I hope so, guys. Yeah. So read this text, and
I have
Isabella, don't fall asleep.
Study, and then more questions were raised. Yeah.
Right, guys. It's technical. It's actually not as hard as it looks. Okay. I mean, it's very hard to understand what it means. I can prove it with certainty, but when I try to interpret what it means, I have no idea. So that's the problem, right? When I prove something with certainty, I don't know what it means. And when I know what it means, I have no idea how to prove it. So Yeah, have a good one. Enjoy your whatever it is.
Yeah, you too. Mhm.
Right. I lost the bet, by the way. It's too bad. John, I think you know what I mean, right? Anyhow, take care.
I have a question. Can I ask a question?
Yeah, go ahead.
Yes. What I was relating this class with the central limit theory, where you have as your sample size increases, there is the bell curve that is normally distributed.
Yes.
Now, what I'm seeing, the only difference with this class with the large theory of numbers is that instead of thinking of bell curve, I'm thinking of average and expected value. So the mean of the example.
So the central limit theorem tells you that that the averages will be distributed in a bell curve, right? So the more you take many of them, they will be distributed in a bell curve, right? The strong law of large numbers or the weak law of large numbers only talk about convergence. They don't talk about the distribution of the actual averages that you will be getting, right? That's
correct. That's the way. Yes, that's the way I am relating this class, because it's normally when we are computing the central limit theory, we divide by the square root of n. But now here for the low numbers, we are dividing just by n.
Right. Well, the reason you divide by whichever number, it has to do with the mechanism of establishing why the result holds, right? So when you establish, so you see, if you go through, you see, it's not arbitrary why you divide by n if you go through the proof, right? You see why it's n in this case. So it would be not arbitrary why you divide by root of n in that situation as well, right? So yes. So we need to talk about, we will talk about the, what do you call it? We will talk about the continuous random variables. I think we'll begin on Monday, and hopefully we will get to talk about that as well.
All right, thank you.
Sure. All right. So what else can I help you guys, those that are still sitting here with me? If you're very polite, if you have to, and I see already more people are leaving, they don't like me, right? Already 9, 10, 8, forget. No need to sit with me anymore. Lonely, poor, lonely Arkady. Nobody wants to meet me. Nobody wants to get infected. So, what can I help you guys?
Can you go back to the proof?
You want to see the proof?
Yeah, that we were talking about.
Sure.
Okay, so yeah, keep going.
Mm-hmm.
The next.
Yeah. Okay. So this is all, and you know, for a mechanism. What is Josh? What is GTG? I have no idea what it means. You know, you're talking to another person. What is GTG? Can anybody tell me? Got to go. I figured it. Yes, you see, of course. Yeah, go ahead, guys. Go. Good luck. Goodbye if you have to go. If not, I'll continue a little bit and talk about whatever is here. Okay.
Okay. So can you explain how did from this point where it's exi squared x2 squared forms into and then forms into
this thing, yes.
Squared. So then it forms into how do you get x1 squared? Like how do you get from that to that?
X1 squared squared? You mean this? Well, because they're independent. So you see this part? X1 squared is independent from x2 squared. So the expected value of their product is the product of expected values. So basically, this would be the expected value of the first times the expected value of the second guy. And because they are identically distributed, it's the same as the expected value of the first guy squared.
But aren't they different? Like
the x1 squared and x2 squared are identically distributed, and they are independent.
Okay.
So so you see, I could have calculated x1 squared, expected value of x1 squared, and multiplied by the expected value of x2 squared. Expected value of x2 squared, but they are the same. So it's the expected value of x1 squared, and that number is squared again, because I have two of them, right? It's just e of x1 squared times e of x2 squared, right? And they are the same, so it's just e of x1 squared squared. So we have that.
Okay.
Right? And then I use, and then what do I use? And then I use variance to tell you that this guy is smaller or equal to this guy. Yeah? And that means that this number is less than m, because this guy is less than or equal to m. This guy is also less than or equal to m. What I need this for is, look at it. I'm adding all those terms. I'm using infinite series. So I'm adding all those terms and I'm getting a convergent sequence. So I'm getting a convergent series, which means that those terms must go to 0. They must, the limit of those terms, the limit of the expected values is 0, right? And it's essentially in this part of the proof, you see. So I'm taking the averages, raising them to the 4th power, and I'm adding up all the averages. If in doing that, I get a convergent series, certainly, always, right? So this summation never ever equals. So if I add up the averages to the 4th power, all of them, I add all the averages to the 4th power, the summation will be not infinite, will be less than infinity 100% of the time. Do you understand? That means, practically speaking, it means no sense to me, because I'm not obviously going to have infinitely many averages. Where do I obtain them, right? But theoretically speaking, the sum of the averages is never going to be infinite, because the expected value is less than infinity. Right? I use this part to prove that the expected value of the sum, we know it's always the sum of the expected value, so we can move e here. So we have from here to here, we have this sentence, and we know that this series is convergent, because this term that I'm pointing at is less than this expression, and that expression is a comparison to p series. It compares it to 1 over n to the cube, to the 3 power, and to roughly 1 over n squared, and both are convergent p series. That means that this summation will be finite. And if this summation is finite, that the expected value is finite, which means that no term here could have ever equaled to infinity with any probability. Okay? David, everybody can go home, right? There's not sure what's on or off. It's just you know, the lesson is over, I think 10 minutes ago. If you want to, you stay. If not, you know, classes are always, you know, if you want to, you come. If you don't, you don't. No problem.
Okay.
Yeah. Take care, David. Go to the other class. Nice to see you. Although you remember, my class is more interesting, for sure, right? What other class do you go to? What's there to be, right? Good. So
what makes I understand what this, like the e Sn over n to the 4th is less than infinity, but what makes that go to 0?
No, if the summation is less than infinity, remember the divergence test. The infinite series can only converge if the terms of the sequence are approaching 0. Right? What's important is essentially this thing, right? So this part is less than infinity, which means that the sum could never have equaled, and none of them could ever equal to infinity, because if each term here, if each e of Sn over n to the 4th, you know, it cannot, if each of them is less than infinity, in particular, yes, in particular, the sequence. Sorry, I lost my tongue here, right? This thing here, this is a random variable. It looks scary and ugly possibly, but it's a random variable, right? It's just the sum of the averages raised to the 4th power. I took infinitely many averages and I raised each of them to the 4th power and I added them up. And the averages are not predictable, right? They can be different values, so they jump around. So because the expected value of those averages is a number less than infinity, with certainty those averages will tend to 0. Because if there is some small probability that the averages do not tend to 0, some of them, then the summation will be infinite. And that means that this random variable has some small probability of taking the value infinity. But if it has a small probability of taking the value infinity, right, what does it mean? If this happens, if this could equal to infinity, the summation were to equal to infinity, the expected value of this random variable is bigger than or equal to one of the terms multiplied by the probability, correct? Because the expected value is all the terms multiplied by probability, and the terms are positive here. That's why I want an even power. It's not so much 4 as it's really an even power makes it positive, because the average could have been less than 0. You understand? By raising it to the 4th power, I'm making it positive. So the expected value here is bigger than or equal than any particular value it can take times the probability it can take, because I add over all the probabilities. But infinity times that small probability, which is not 0, is infinity. And that's a contradiction. We got that it's less than infinity, which means that this summation with virtual certainty never equals to infinity, which means with virtual certainty, the terms of the sequence go to 0. Right? And if the 4th power of this goes to 0, that means the number also goes to 0. The number inside of the 4th power also goes to 0. And by this roundabout way, I don't really care about the 4th power. I want this to go to 0. So I just raise it to the 4th to produce an infinite series. The infinite series then concludes that this goes to 0, and that concludes that this goes to 0 with probability 1. And if the average isn't 0, I just adjust. I just create random variables yk, which is xk minus mu. So that means I'm just shifting them so that the average now is 0. I'm relabeling the random variable. And then that's the same. So if yn, the average for yn goes to 0 that with certainty, that means the average for xn goes to mu with certainty. Okay? So that's the idea. You just have to go through that proof, read it through, and hopefully that makes sense. Good?
Yeah, that makes a lot more sense. But can you just explain the phrase what with probability of 1 means?
No, that's the truly difficult part for me to explain, because you see, I try to use this language. Probability 1 in everyday language means certain, right? So this limit will certainly go to 1. However, as I mentioned, probability equal to 1 does not mean that something never happens, right? So that makes it more complicated in that sense. So you know, in any normal discussion, when you say, well, 100% certain, that means it always happens, right? But to my mind, 100% certain means you know, it depends how you interpret probability, right? It does not mean to my mind that it never happens. It just means it happens extremely infrequently. Or with the thing is, you see, for something to have probability equal to 1 and not happen all the time means that the outcomes where the outcome does not happen are becoming very, very sparse. So it's like this example, right? If I say the probability that you will live 1,000 years is 0, and you might be, if you're not an optimist, you will be upset. Well, I cannot live more than 1,000 years. But Methuselah in the Bible lived more than 1,000 years, right? So Methuselah is one individual, and maybe there would be infinitely many individuals that just have to be infrequent because we are taking a limit. Right? In every ordinary sense of the word, you see, whenever you see an outcome, because everything you see seems to be finite, correct? Everything. So the number of people that ever lived is maybe a big number, but finite. So if there was one person that lived more than 1,000 years, if I just take one person over the total number of people, that might be a very small number, but still somewhat different from 0, correct? But the idea is that if you have infinite populations, or then you can have some individuals that live more than 1,000 years, and yet the probability will still be, because you take those individuals and divide by the total, and it will be just 0 because the total is that big. Yeah. So it's a limit concept, you understand? So in the practical sense of the word, you always deal, it seems, with finite numbers. But in the theoretical sense of the word, if the population is infinite, you might have quite many Methuselahs. You might have quite many people that live over 1,000 years, infinitely many of them. Yes, Andrew, you got tired of philosophy, I guess.
Okay. Right. So when you're saying probability of 1, that means it's guaranteed to happen. Well, not guaranteed, but like
that's the thing. You see, that's why it's such a problem, right? I say, you see, in every common expression, you know, of this word that you're saying it's guaranteed to happen. But if you believe in infinite populations, or if you believe in the limit actually going to infinity, then it is not. Yes, it is not. Take care, John. It is not guaranteed to happen, right? In that sense, but practically speaking, usually you have them. Probability tends to be kind of uniformly distributed. In other words, you expect that if it's a zero probability, that you just don't see it. If it's non-zero probability, then you see it at certain intervals, more or less, right? So if you take a big enough finite interval, you will see that outcome with very sure certainty, right? So when you toss a die, you know, you don't think that you would throw it 1,000,000 times and you don't see one, right? So if you throw it 1,000,000,000 times, you're virtually guaranteed to see a one, right? Because, or if something has probability 0, then the only way outcome can happen and probability still be 0 is that the outcome becomes less and less frequent. In other words, it's less and less often. So you might have one Metushellach in a while, just like in the sequence of Bn, they become less and less often, right? So you have ones and zeros, but the ones become less and less often. So that tends to not happen when you consider what you call it wild natural probability, because you think that would indicate that the probability is changing for some reason, that something is making it different, right? So like almost conscious probability, where you know where something is happening, so it's no longer the same experiment. So you can interpret it this way. So to make it simpler, you might say it guarantees that the outcome happens. Probability 1 means it's always happening.
Okay.
Don't worry, I will confuse you on Monday.
Okay, thank you.
Take care.
You too.